again, hello and welcome to everyone to our meanwhile 22nd edition of our virtual seminar on precision physics and fundamental symmetries. It's a great pleasure to welcome today's speaker, Professor Dave DeMille from Yale University, who will be talking about cold molecules for tests of fundamental symmetries. Dave graduated in 1994 at UC Berkeley, studying nearly degenerate opposite parity levels in atomic dysprosium for the study of parity non-conservation. After different career steps via BNL and Amherst College, he was appointed as associate professor in Yale in 1998, where he became full professor in 2004, a position he still holds today. Dave has dedicated his entire career to the study of violations of discrete symmetries using ultra-cold polar diatomic molecules. For example, his group was the first to accomplish laser cooling of diatomic molecules, achieved in 2010 using strontium monofluoride. He's also one of the driving forces in the very famous ACME collaboration, which constrained the upper bound of the electron EDM to a level of 10 to the minus 29 electron centimeters using thorium monoxide. For his work, Dave has received numerous research prizes, for example, the 2006 Pipkin Award for wide-ranging studies of fundamental symmetries in atoms and molecules. So Dave, we are very happy that you are here today to give a talk in our seminar. We are all looking forward to it. And with that, I leave the audience to you. Thanks very much.
Great. Well, thank you very much for the extremely nice invitation, Stefan, and our extremely nice introduction and the invitation to speak. It's a real pleasure to be here. What I'll be telling you about today is, in some sense, a broad overview of how to use atomic molecular optical systems, but particularly molecules, to explore discrete symmetries such as parity violation and CP violation. But sprinkled in with the broad overview will be some recent results and recent progress from our group. So one of the things that I'll be emphasizing is that all of the techniques that we're using are in some ways analogous to atomic clocks. And there's a good reason for this. This is really the longest running type of technology based on quantum mechanics. It's been extraordinarily successful with continuing very rapid progress in the field. Of course, the first clocks were built by Norman Ramsey and colleagues, but I'll just point out that until the late 1990s, that late in time, the state of the art for atomic clocks was still done with thermal atomic beams. And it's really only been in the last 2 decades or so that laser cooled atoms have become the better technology for more accurate clocks. In large part because of the success of atomic clock technology, I think the entire atomic physics community has agreed without Shallow's dictum that you should never measure anything but frequency. Of course, frequency is always equivalent to energy or time or phase. So in all the measurements I'll be talking about, we're essentially measuring some energy splitting or a shift in an energy splitting between two levels in an atom or a molecule. And the figure of merit for precision on these, everyone in atomic physics is familiar with. There's some quality factor that tells you how sensitive your system is to what you're trying to measure. So it's good to choose a system with a high sensitivity. But in addition, you want a long coherence time of the superposition state that you use in the clock-like measurement, and a good signal to noise, which of course the standard quantum limit of signal to noise for n uncorrelated systems is the square root of n. So the theme of my talk is really to talk about using molecules in particular, but also atoms as a sort of transducer for interesting physics signals in particle physics and nuclear physics. And the key observation here is that electromagnetic interactions define ordinary matter, but they also obey discrete symmetries such as parity and time reversal and charge conjugation. But it's been known for a long time that weak interactions can break these symmetries, and in particular, it can break parity symmetry and the combination of C and P. And breaking these symmetries can induce certain types of characteristic energy shifts in atoms or molecules. So an example is the left and right-handed enantiomers of chiral molecules, because of the weak interaction, the ordinary weak interaction, are expected to have very slightly different energies. This has not been measured in any system yet, but it's a very clear example of what it means to violate parity. In addition, a charge distribution along the spin of any particle, shown here is, for example, the dipole moment of a neutral particle with a little negative charge here and a little positive charge here aligned with the spin. That also violates parity as well as time reversal symmetry. So the thing to keep in mind here is these symmetry violating signals in atoms and molecules act as a sort of background free probe for new physics. It means that you don't necessarily need to make an extremely accurate measurement. You only need to make a very sensitive measurement, which is still hard, but not quite as hard as making absolute accurate measurements. And you notice the asterisk, we'll see there are some caveats to this. So let me just dive into one of these, which is talking about parity violation. And parity violation historically has been measured in atoms and used as a probe of the properties of Z0 bosons. So this is really historically very important. It was one of the first places where violation of discrete symmetries was used, taking advantage of AMO methods to add new interesting information to the study of electroweak interactions. So of course, in particle physics terms, as I said, ordinary matter is described by electromagnetism, chiefly the Coulomb interaction between electrons and nucleons in an atom. And of course, we know the eigenstates of these for a simple single electron atom are sp, d, and so on states with alternating parity, even, odd, and so on. But in addition to this, in addition to the ordinary Coulomb interaction, there is also an electroweak interaction associated with virtual exchange of Z0 bosons between the electrons and nucleons in an atom or in a molecule. And the weak interaction is fundamentally different than the electromagnetic interaction because this Z0 exchange can break parity. And in particular, what this means is an S state is no longer a pure positive parity state, but it turns into mostly an S state, but with a tiny admixture of an odd parity P state. That's the meaning of parity violation in terms of atomic wave functions. For many years, the goal of atomic parity violation experiments was to measure what's called the weak charge. And here you may notice that the Coulomb interaction is described by the quantities, the charges of the particles, which is a sort of coupling strength, an electromagnetic coupling strength for each particle. In weak interactions, each particle has two distinct types of coupling strengths. There's a vector coupling, which is completely analogous to the charges, but can be different for different particles. And then there's another quantity called an axial coupling, which is explicitly linked to the spin of the particle. So it's, from the language, it's not surprising that the coupling of the combination of an axial coupling of an electron and a vector coupling of a nucleus gives rise to parity violation, because an axial vector times an ordinary vector is odd under parity. And this particular quantity, the product of these two coupling constants, the axial electron coupling and the vector nucleon coupling, is called the weak charge. And this mixing coefficient, determined by parity violation, is equal to this coupling constant times some factor that can be calculated from electron wave functions. And typically in atoms, this can be calculated to a percent or better. The interest here for many years was to look to see if this coupling constant was exactly the same as predicted by the standard model, given a known electron wave function factor and the predictions of the standard model for these coupling constants. Or if it deviated from that, it could be evidence that there's a new particle analogous to the Z, a Z prime particle, with different couplings that would modify this mixing coefficient. So how does this work? Well, as suggested before, you can look for this parity breaking by putting your system, your atom or your molecule, in a handed environment. One example of such a handed environment is 3 vectors determined by the electric field, a static electric field, a static magnetic field, and a laser helicity. And by switching this from a right-handed to a left-handed configuration, you can look for an energy shift in an atom or a molecule that should only occur due to parity violation and the weak interaction. And the most famous example of this was an experiment done by Carl Wyman's group that was published over 2 decades ago now, where they used a thermal atomic beam of cesium atoms interacting in an electric field and a magnetic field in a very intense circularly polarized laser beam. This result from Carl Wyman's group resulted in a measurement of the weak charge with a 0.4% accuracy. And it could be interpreted, this electron wave function factor was calculated to 0.3% accuracy. So altogether, that led to a test of whether this coupling was the same as predicted in the standard model at the level of about 0.5%. And this was really competitive with things that came before from particle colliders in terms of what limits it could place on the existence of new Z prime bosons, and also on how a parameter of the electroweak theory, the weak mixing angle, changes as a function of energy. And this is the plot of the running of the sine squared of the weak mixing angle versus momentum transfer. So the end of this program, which was really the culmination of nearly 15 years or so of work of many groups in the field, was a measurement that agreed with the standard model. It still is powerful enough to constrain interesting new physics, even in the 20 years since, and the progress across all of particle physics since. But the trouble with this is it's no longer background free. So the ability to determine whether there's new interesting physics associated with this is really limited by the ability to calculate these electron wave function factors. And at least to date, there's no pathway known to be able to do much better than previously. So what I'll tell you about is a new set of experiments we've undertaken, which is also looking at parity violation, but a different aspect of parity violation. And that is, rather than this weak charge, which is associated with the axial electron and vector nucleon couplings, we're looking for something that we call nuclear spin-dependent parity violation, which comes from the coupling of the electron vector coupling and the nucleon's axial coupling. This effect turns out to be something like, depending on the particular system, 30 to 1,000 times smaller than the weak charge effect. And in addition, so it's tiny, it's hard to measure. In addition, the axial nuclear charge turns out to be very strongly renormalized by strong interactions between nucleons or between quarks in a nucleon. So this is not only hard to measure, but it's hard to calculate, because it relies on low energy QCD, which is non-perturbative theory. In addition, the story is complicated by the fact that in heavy nuclei, where there are many neutrons and protons inside the nucleus, there's what appears to be a second order effect associated with the exchange of Z and W bosons between protons and neutrons in the nucleus, which also is parity violating interaction. It deforms the nuclear shape to create a handedness, which turns out to take the form of a current flowing in the shape of a helical toroid. That the magnetic field of this helical toroidal current can interact via sort of hyperfine interaction with the electron, an ordinary magnetic interaction. And this gives a signal which is indistinguishable from this signal. So there's a lot of physics going on here, and it's all small and hard to measure. So in fact, these two effects have to be thought of as one unified effect that can be measured in any particular atom or molecule with an electron and a particular nucleus. The actual form of the Hamiltonian, won't try to say much about this except for the fact that it has, so it has two terms of the same form. This one from the direct Z exchange and this one from this nuclear effect called an antipole moment. It mixes opposite parity hyperfine states differently depending on which hyperfine state it is. In the end, the physics is encoded in the matrix element of this Hamiltonian, which can be written as the sum of these two coupling terms times, again, an electron wave function factor that can typically be calculated quite accurately. Okay, there we go. It's also worth pointing out this electron wave function factor scales with the charge of the nucleus, Z squared. So the effect is much bigger for heavier systems. But these two coupling terms, the nuclear antipole moment effect, also grows rapidly with the nuclear charge. So that if you're interested in this first term, which is arguably more fundamental, then you have to be able to measure very light systems so that this term does not dominate. But if you measure heavier systems, you'll learn about these nuclear antipole moment couplings. In the end, what measurements of this type, of this particular effect would tell us is how QCD modifies weak interactions. So for example, if we're able to learn about the Z0 exchange terms, we learn about some particular coupling constants in electroweak interactions, which are only poorly measured. These can be related to fundamental electron quark couplings using QCD again. And there's been a tremendous amount of work in this direction using electron colliders, sort of GeV or higher energy scales. And this plot shows the state of the art for this field. This axis shows these new couplings we've been talking about, the vector electron axial nucleon couplings, in this case framed in terms of up and down quarks. And you may be able to see on this plot, the standard model prediction for this is in some dimensionless units, minus 0.1, and the uncertainty on this is about minus 0.08. So essentially these couplings are almost unmeasured in the standard model at this point. So there's still something about the electroweak physics which is almost entirely unmeasured. In addition, it's been suggested that these couplings could be calculated by lattice QCD methods. This would be quite interesting because to date, everything that's been calculated by lattice QCD is in some sense not a prediction, but a postdiction. It's almost always calculating things that are known in advance. So if lattice QCD people could calculate this, which seems plausible, then we could have an actual prediction verified by experiment or not, as the case may be. This program requires measuring the effect in very light systems where the signals are small. In heavier systems where the signals are much bigger, we definitely expect to be able to measure nuclear antipole moments. These tell us about the weak electroweak couplings between nucleons, which are still poorly known despite 50 years of effort. And in the end, the technique that I'll tell you about looks like it'll allow us to create a sort of table of antipole moments, analogous to a table of nuclear magnetic moments or nuclear electric quadrupole moments. This is really a unique property of each nucleus, of which only one has been measured by Carl Weinman's group, and his measurement is in very poor agreement with theoretical predictions. So yeah, it's really, there's a lot of space to cover and very little known there. So I'll tell you now about an experiment that we call zombies. Here are the folks who worked on zombies. I'll apologize to M&A if she's watching. I don't know what happened to that photo. We're using molecules as a way to amplify the signals from this particular type of parity violating effect, the nuclear spin dependent parity violation effect. And as always, what leads to the new physics is the mixing between even and odd parity states. And of course, just from simple first order perturbation theory, you know that that mixing coefficient is the matrix element divided by an energy denominator. In atoms, so in experiments such as Carl Weinman's experiment, this energy denominator is order EV. In molecules, there are opposite parity states associated with rotation, which are much closer together, order 10 to the minus 4 EV, and that seems like it's an advantage. It gives you 4 orders of magnitude larger mixing. But we go further than that and use the fact that by applying a magnetic field, you can Zeeman shift an even parity state and an odd parity state to essentially exact degeneracy. This usually takes magnetic fields on the order of a Tesla, which is technologically not so bad. And in the end, we get an effective energy splitting here, which is something like 10 to the minus 11 EV. So this enhances the mixing by this incredible 11 orders of magnitude compared to the old experiments with atoms. Here's where we actually go about the measurement. We start with a molecular beam. In this case, barium fluoride is our first target system. The molecular beam is relatively cold, but still these even and odd parity states are of such low energy that they're both equally populated in the Boltzmann distribution. The molecules then fly from left to right into a superconducting magnet that determines the magnetic field that tunes them to degeneracy. Before any real interactions, they're hit with a laser beam that optically pumps one of these states to deplete it and leave it empty. The molecules then enter a region where a series of ring-shaped electrodes with distributed voltages are used to apply a magnetic field that in the molecule's frame varies over time. At the end of that electric field interaction, the sum of the population will have been transferred into the previously empty state. And then outside the magnet, we again use laser-induced fluorescence to empty this state, and we detect the resulting fluorescence when that state is pumped. So the basic idea is fairly simple. It means that we need a region in the center of the magnet, which is about 5 centimeters long and about 1 centimeter in diameter, where the Tesla order of magnetic field is homogeneous at the 10 to the minus 7 level. And it turns out that the electric field that's useful for us to apply is a single cycle of a sinusoidal oscillation. Again, this is applied spatially, but as the molecules fly through it, they see as a temporal variation in the electric field. So here's the energy level diagram of the system. We have these two states, one populated, one empty at the beginning. They're separated by some energy gap delta, which we can tune with a magnetic field. And we apply an oscillating field, oscillating electric field to the system, which is a sinusoidal oscillation. Its frequency is deliberately far above resonance with a system. So it's not a resonant driving, but a far above resonance blue detuned driving. And what we're interested in is measuring this matrix element W that encodes the physics of interest for the weak interaction. And the two-level system has a simple Hamiltonian, which is easy enough to diagonalize that I gave this as a problem to my undergraduate students. If you solve this, you'll find that at the end of this single cycle pulse, some of the population is transferred to the previously emptied state. And the population in that state has a particular form which allows us to make the measurement. There's one term which does not depend on the sign of the electric field that we apply. It's what we call the Stark term. And then there's another term that comes from interference between W and the Stark mixing, which gives us a term which is odd in the electric field and also linear in the electroweak matrix element W. So with a signal like that, we can measure these signals with either a positive value of E0 or a negative value of E0. And we can form an asymmetry, which is the difference between those signals over their sum. And this is a quantity that's linear in W and only depends on other factors that we know because we apply them in the experiment, omega or delta or the strength of the electric field. And notice this is a dispersion-like function of detuning. It blows up near zero detuning and then falls off like 1 over detuning. One of the interesting things about this method is that the statistical uncertainty on this matrix element of interest, which after all is an energy, this statistical uncertainty has the same form that you would expect for the uncertainty of measuring a frequency in a clock. It has the usual 1 over observation time or coherence time quantity or scaling, the 1 over the square root of the number of detected particles scaling, and some numerical factors that are just from definitions. So it turns out that you can recast this entire procedure in the form of equivalent to measuring an AC Stark shift. And this was really pointed out back in the 90s by Norval Fortson, that these parity violation measurements are really indeed nothing other than measurements of an energy shift, which is equivalent to an AC Stark shift. So we've now published results from this. We ran a proof of concept run where we made a measurement with barium fluoride molecules. In this run, we used barium, an even isotope of barium with no nuclear spin, so it can't give any nuclear spin dependent signal. In principle, there could be a nuclear spin dependent signal from fluorine 19, but the calculations indicate in this case, this is an entirely negligible size effect. So this was a way to test for systematics by taking data and seeing, did we get the answer that we knew was correct, which was 0. So in the end, we were able to measure this matrix element with an uncertainty of about 2 hertz. It was consistent with 0. Here's a typical data run of the asymmetry versus detuning. And the red is a fit to this dispersion-like shape that would be expected. So the bottom line from this is that in this proof of principle run, we achieved a sensitivity which is 60 times better than the prior best from Wyman's experiment at Gila when measured in terms of energy shift. And this turns out to be sufficient to measure this nuclear spin dependent parity violating effect in many different nuclei as soon as we install some technical upgrades, such as a better molecular beam source. And just to give you a sense of how powerful this is, with molecules containing all the nuclei in red here, we should be able to make a 10% measurement with less than an hour of data with the improved molecular beam source. The ones in blue with the same statistical sensitivity, we would be able to do better, but require control over systematics. That's about an order of magnitude better than we demonstrated. And with the purple ones going down to very light nuclei like lithium and beryllium, we think we can get enough statistics to measure the effects here, but we'll have to really improve the systematics beyond what we were able to demonstrate so far. We think that's plausible, but it's clearly going to take some work. So the bottom line here is that this method looks like it will make it possible to really start to compile a table of antipole moments and measurements of these fundamental vector electron axial quark couplings and really open up a new window into electroweak physics. So with that, I'm going to switch gears and start talking about a different class of experiments, which are loosely referred to as electric dipole moment experiments. So the point here is that any sort of charge asymmetry along a spin axis of any particle violates time reversal symmetry, because if you reverse the direction of the spin axis changes, but a static charge distribution doesn't get affected by changing the direction of time. So if a particle has any sort of charge asymmetry locked to its spin axis, then time reversal is not a good symmetry of nature. And according to the CPT theorem, which is a theorem that holds for all quantum field theories, which is to say all theories that we know something about or that so far have been successfully applied to physics, particle physics systems, T violation is equivalent to CP violation. So I'll often interchangeably use the terms T violation and CP violation. Of course, this effect also violates parity because the charge distribution is a polar vector that changes sign under parity. The spin is an axial vector that does not. So much like for parity violation, atoms and nuclei can act as a sort of transducer of CP violating physics. For example, if there's some new exotic particle exchange between electrons and nuclei, or the up or down quarks in the nucleus, that gives rise to a CP violating atomic Hamiltonian. There can be effects such as virtual exchanger particles that create an electric dipole moment of the electron, or virtual particles, new exotic particles that cause quarks to have electric dipole moments, or even the strong interaction version called a chromoelectric dipole moment. This deforms the nucleus to give it what's called a shift moment, and again leads to some CP violating atomic Hamiltonian. So these different effects, in the end, the electron EDM, this nuclear shift moment, which comes about due to CP violation somewhere in the strongly interacting sector, and the direct electron nucleus CP violating interaction, these all have the same effect, which is to say, if you start with an atom in an s orbital and then consider the effect of an electron electric dipole moment, because of this charge distribution, the part of the wave function above the nucleus will be repelled from the nucleus, pushed away, because the positive charge of the dipole is closest to the nucleus. The part of the wave function below the nucleus will be attracted to the nucleus because the negative charge of the dipole is closest to the nucleus. That will lead to a deformed electron wave function that looks vaguely like this. Likewise, a nuclear shift moment is equivalent to an electric field internal to the nucleus, which pushes the electron wave function up. And same with this CP violating electron nucleon interaction. All of them result in this sort of deformation of the atomic wave function. And this deformed wave function, it's easy to see is, again, a mixture of S and P states. So you can just visually see a superposition of S with a little bit of P state through constructive interference gives you more amplitude above the nucleus, and through destructive interference gives you less amplitude below the nucleus. Again, much like in parity violation, this mixing coefficient grows very rapidly with the atomic number Z. Here it's for somewhat different reasons. It's because of relativistic effects, stronger Coulomb fields, increasing nuclear size, and so on. But like any interaction that mixes S and P states, there's no energy shift to first order. There's no diagonal matrix element. There are only off-diagonal matrix elements. This field-induced polarization, or sorry, this sort of polarization can also be induced by a static electric field. Again, you can see this electric field will push the electron wave function up and lead to this sort of deformation, which is again a mixing of S and P states. So much like the CP violating interactions, the ordinary Stark effect leads to no first order energy shifts, but it does induce a dipole moment. It deforms the wave function. And we're going to talk about a quantity we call the electric polarization, which is just how much dipole moment there is induced by the electric field that causes this deformation, divided by the maximum possible dipole moment that you would get if you fully mix these states. So the way to make a measurement of these CP violating effects, much like was the case for the weak interaction, is to do some sort of Stark interference. So in addition to the CP violating interaction that mixes S and P states, we'll also deliberately apply an electric field that mixes those states. Again, in a toy model with only 2 levels, you get a simple Hamiltonian, which you can diagonalize by hand. You can see that if there's no CP violation, the electric polarization for small fields is linear in the field, and for large fields is just 1 times the sign of the electric field. The interference between these 2 terms, when you diagonalize the matrix, you'll always have to square these off-diagonal matrix elements. There'll be a cross term between the electric field term and the CP violating term. The energy shift due to this CP violation is equal to this electric polarization times the actual interaction of interest. With atoms, because the energies are so far apart between S and P states, typically you can only achieve a polarization on the order of 10 to the minus 3 or 10 to the minus 4 by applying the strongest electric fields you can in a lab. By contrast with molecules where the energy opposite parity states are much closer together, you can get essentially complete polarization and a maximum energy shift due to the CP violation. So to give you an example of the physics that can lead to CP violation, it turns out that in the standard model, the electron has an electric dipole moment that's not 0, but it's extremely small. It happens only due to 4th order Feynman diagrams like this one. These diagrams sum up in a way that cancels the contributions from all of them to high precision, but not exactly. They all depend on the one CP violating effect that's known to exist in the standard model associated with mixing of quarks. And the standard model prediction for the electron EDM is roughly 9 orders of magnitude below the current limit. So unlike parity violation, these CP violating effects are really truly background-free probes of new physics unless we can make many, many orders of magnitude improvement. Once we're able to measure an effect that at the level predicted by the standard model, then progress for detecting new physics will be much harder. And just to give you a sense, I won't go through this argument carefully, but the electron EDM can be induced by the virtual exchange of some new particle, new heavy particle, unknown to us so far. And with some reasonable assumptions for the coupling strength and the CP violating phase, we find that already the current experiments that I'll tell you about are limiting the mass of this particle to be above about 30 TeV, which is above the energy that's hit by the Large Hadron Collider. So the way these experiments work is pretty simple. We use optical pumping effects to polarize the spins of the particles of interest. We apply a magnetic field for technical reasons, and the spins process around that field, or equivalently have an energy shift between spin up and spin down. Then we apply an electric field parallel to the magnetic field. If there's an electric dipole moment or some analogous effect, that will shift the energy splitting between spin up and spin down. And then we flip the electric field back and forth, looking for a correlated change in the energy splitting between the spin up and spin down states. And just as before, the figure of merit for this sort of measurement, for the statistical sensitivity, depends on how big the electric field or how big the polarization you apply, depends on the coherence time of the spins, and on the square root of the number of particles, which is a counting rate times an interaction time. So as Stefan mentioned in the introduction, we've been working on this for a while in our ACME collaboration, which is collaboration between my group and the groups of John Doyle and Jerry Gabriels. We've had a fantastic group of students and postdocs working on this. This is the group from the latest generation, ACME 2. And here we take advantage of this, effectively the big polarization that's available and using a very heavy molecule, thorium oxide, to get big relativistic effects. So inside the molecule, inside this particular molecule, it's as if the electron were being subjected to an electric field, an effective field of 80 gigavolts per centimeter. So this is really an amplification that's associated with the very high polarization of this sort of molecule. And really using molecules has been a big advance. It means we can now look for effects, energy shifts that are 3 to 4 orders of magnitude larger than what could be seen in an atom. So here's a schematic of the ACME experiment. It starts with a cryogenic beam of thorium oxide molecules. The beam goes through a series of lasers and microwaves that cool the rotational moment to cool the rotational states in order to accumulate population in a single rotational state. Then enters an interaction region where lasers are used to pump the system into a metastable triplet state with an unpaired electron spin, and then to spin polarize that state. Molecules then fly through an interaction region of about 20 centimeters for about a millisecond. And then we use lasers to detect the spin orientation via polarization dependent scattering and pick up the laser-induced fluorescence in photomultipliers. In ACME 2, the latest generation that has given a result, compared to the first generation of ACME, we increased the acceptance of molecular beam to increase the signal by a factor of 8. We prepared the states in a more efficient way to get a factor of 12 more signal. And we detected in a more efficient way to get 4 times more signal. So a huge increase in signal from one generation to the next. Here's to give you a sense of the apparatus. Here is the molecular beam source, magnetic shield end caps, interaction region, vacuum chamber, electric field plates, magnetic field coils, the whole system buttoned up in its magnetic shields. And as for most atomic physics experiments, we have several tables full of lasers and optics. So the end result of all of this is what our signals look like is a spin rotation signal that tells us the angle of the spins relative to the angle of the polarization of our probing lasers. And essentially we park the parameters of the experiment here, and then we start flipping the electric field back and forth. If the spin rotates due to an electric dipole moment, then we'll see the signal go up and down this slope. So to make a long story short, the end result of these experiments, like basically any precision measurement, is a error budget. Here, all the numbers are in units of frequency microradians per second. So a couple of things to notice: the systematic shifts that we were able to measure were tiny compared to the uncertainties in the systematic shifts. So essentially the systematic shift was zero. And the uncertainty was mostly statistical, with a roughly comparable amount from systematic errors. In the end, this gave us a total uncertainty of about 500 microradians per second, or a little below 100 microhertz. And this can be interpreted in terms of an electron EDM, which is given by these numbers. It's consistent with zero. And that allowed us to set for now, the world's best upper limit on the electron EDM at less than 1.1 times 10 to the minus 29. So about an order of magnitude better than our prior measurement. To give you a sense of some of the physics impacts here, for example, this sort of scalar particle exchange could also give us the effect that we measure in addition to the electron EDM. So we can set limits on either or both of these. If you are interested mostly in this, our result actually shows that particular particles of this type, known as scalar leptoquarks, have to have a mass of over 1,000 TeV, so 10,000 times larger than the Higgs boson mass, which is quite remarkable. Another way of looking at this, one of the main drivers for looking for electric dipole moments has been that there have been predicted to occur in supersymmetric theories. So this is a plot taken from Jonathan Feng that shows on the x-axis different supersymmetric partner particles of all the known standard model particles. Over on the y-axis is, in a log scale, the mass of particles. Over here are the masses of the two heaviest standard model particles, the top quark and the Higgs boson. The blue lines show what the LHC has ruled out. So only above the blue lines was allowed by the LHC back in 2013. The green lines were what this particular version of supersymmetry, a fairly generic version, we're predicting in terms of where the supersymmetric particles should appear with mass below the green lines in order for the theory to look natural. You can notice that the Higgs mass already provides some tension. It's higher than it was expected to be in supersymmetric theories. So I've done my best to update this plot. The LHC limits from about 2018 definitely improved. Also point out that one of the things that this theorist, Jonathan Feng, says in this paper is that all of the constraints shown are merely indicative and subject to significant loopholes and caveats. So of course, particle physics theorists don't really know what comes after the standard model. So everyone has to make assumptions about what's reasonable. But these are fairly generic assumptions for supersymmetric theories. If we make the assumption that CP violating effects in supersymmetry are about as big as they can be, which there are substantial reasons to expect, but there are no guarantees, then the ACME result has put these bounds on several supersymmetric particles. And you can see the bounds that ACME places are well above the bounds from the LHC in the cases that we're sensitive to. And in fact, they're not only above the reach of the LHC so far, but they're above the reach that the LHC ever anticipates getting to. So we're really on the cutting edge of particle physics with these experiments. We're now trying to improve ACME. We're building the third generation ACME 3. The main improvements we're going to use is an electrostatic molecular lens, where we calculate that we'll get 16 times more molecules. It's complicated. We have to move the molecules into a different metastable state to focus them and then back out of that metastable state. But all the properties of that state have now been verified in our lab. We've also verified that the metastable state where we do the measurement has a longer lifetime than we had originally believed was true. So that means we're going to have a longer interaction time, about 5 times longer, just by extending our interaction region. And we'll detect more efficiently using silicon photomultipliers instead of ordinary PMTs. We've also eliminated a technical noise source from ACME2. The bottom line is that we're expecting a factor of 10 or 20 improved sensitivity within the next few years, 4 years or so. Also point out that ACME is by far not the only EDM experiment in town. There are also experiments looking at nuclear shift moments, which are essentially the nuclear analog of an electric dipole moment. And in particular, the experiment done at the University of Washington, Blaine Heckel and colleagues using mercury 199 atoms is also sensitive enough to push above the bounds set by the LHC. So these are really complementary experiments, electron and nuclear EDM experiments. They test different parts of where new physics could appear. And this is generally true. I won't try to go through this in detail, but starting from any sort of fundamental CP violating phases due to some new physics, that can show up in leptons like the electron and give an electron EDM or something related. But it can also show up in hadrons. For example, if there's CP violation inside quantum chromodynamics or some new interactions due to supersymmetric particles or other exotic particles that haven't been detected. These can give neutrons and protons EDMs. Those cause this deformation of heavy nuclei called a shift moment. And these cause EDMs of diamagnetic systems like mercury or radium atoms, but also diamagnetic molecules such as thallium fluoride. And with this motivation, we've started a new experiment that we call Centrex. It's a collaboration with Tanya Zelevinsky, Dave Kewal, and Steve Lamoureux to look for nuclear shift moments using the advantages of molecules. So again, compared to mercury atoms, we can polarize these thallium fluoride molecules to get a sensitivity, an intrinsic sensitivity that's 4 orders of magnitude larger than in mercury. Thallium fluoride molecule, there's a long history of doing experiments of these that ended about 20 years ago because the technology had reached its limits. But we've now shown that this particular molecule has some nice properties, atom-like properties. In particular, it has an optical cycling transition that should make it easier to detect and even cool than a typical molecule. It has some other nice features, but the bottom line is we're going to try to use this intrinsic enhancement from the polarizability of molecules plus this cycling behavior to push the boundaries on measurements of nuclear shift moments. Here's this plan schematic of Centrex. You can see that it looks quite similar to ACME, and it's really taking advantage of a lot of the lessons that we've learned from ACME. And much like ACME, this has, we're doing a relatively simple first generation, but there are opportunities for future generations that would include laser cooling and possibly even trapping of the thallium fluoride. So here are all the folks working on Centrex. Just to give you a sense, it's starting to come together. We're building the pieces as we speak. So the bottom line with Centrex is we're projecting an improvement of factors of 5 to 10 in parameters, 5 to 10 or 20 in parameters like the theta parameter, which encodes the strength of CP violation in the strong interaction, or on the proton electric dipole moment. So this would put us certainly competitive with, or even better than the best existing experiments measuring the EDM of the mercury atom or of the free neutron. So just to point out, the 3 most accurate AMO type experiments looking for EDMs, or our ACME experiment looking for the electron EDM, the Seattle mercury experiment using vapor cells of mercury to measure the mercury nuclear shift moment, and then the beautiful experiment being done at Gila using trapped hafnium fluoride plus ions, which is, your sensitivity is close to that of ACME. All these experiments have upgrades ongoing now. They've all been underway for many years, but it's sort of striking in the world of atomic physics. None of these experiments uses laser cooling at all, just like old atomic clocks in the 1990s. The Gila experiment at least has trapped particles. That's the first EDM experiment to take advantage of that. And the last 4 electron EDM limits have all been set using molecules, meaning this enhancement from molecules, we're finally able to take advantage of that based on new experimental techniques. So it's easy to get excited about the fact that it's now increasingly possible to cool and trap molecules. And there are 2 different pathways to do this. One is to assemble molecules out of ultracold atoms, techniques pioneered at Gila and now being done in many different places, where it's now possible for many different molecular species to assemble them from molecules at temperatures of below 100 nanokelvin and with high density, culminating at Gila now with Fermi degenerate gas of polar molecules. But in parallel, my group and many others have been developing techniques for direct laser cooling and trapping of molecules. It's not as advanced so far, but it's moving quickly. So the promise of this, just to give you a sense of what one could imagine doing for an EDM experiment with molecules trapped in an optical lattice, if you take some optimistic but not crazy goals, such as a spin coherence time of 10 seconds, near unit detection efficiency, and 1 million molecules in a lattice, this would push you up to 1,000 or even 10,000 times the sensitivity of ACME, and therefore 30 or even 100 times the reach in masses. And one can even dream about applying some spin squeezing techniques to improve the sensitivity beyond the standard quantum limit. So what do you need to make this work? You need a molecule that has a heavy atom in it, a large Z. It has to be easily polarizable. It needs to have electrons in the right sort of orbitals, and you need to be able to make it ultra cold. So there's been a proliferation of ideas for how to do this, and experiments that are launched trying to do this using ytterbium fluoride, barium fluoride, ytterbium hydroxide, radium fluoride molecules at many different places. This is a very exciting time in the field, as so many people are pushing to try to implement this sort of vision. But it begs the question, why not use assembled molecules instead of directly trapped and cooled molecules, because the assembly techniques are more advanced. So an observation is that all the molecules that have been used successfully so far are ionic bonds, strongly ionically bonded molecules, which is really necessary for this large effective internal field. And it's hard to find a laser coolable atom that you can assemble into a molecule that would make a strong ionic bond, except for one, which is the silver atom. This was trapped and cooled over 20 years ago and then abandoned because there was not a strong motivation to do anything with it. But it's really an alkali-like atom that can be handled much like an alkali. Working with Timo Fleig at Toulouse, we found, I would say, an existence proof for molecules, assembled molecules of this type, which are silver radium molecules. So silver has been cooled and trapped. Radium, which is an alkaline earth-like atom, has also been laser cooled and trapped. A series of beautiful experiments at Argonne National Lab. And the long-lived isotope can be obtained in macroscopic quantities. We expected going in that the ground state of silver radium molecules should have a large E effective and should be easily polarizable. And in fact, that's turned out to be the case. So Timo's calculations have shown us that the effective field in this sort of molecule is 65 gigavolts per centimeter, and it only takes a couple hundred volts per centimeter to effectively polarize it. So we're excited about the prospects for using this as a different way to do this sort of ultimate EDM experiment. And with that, I'll just wrap up and use this figure again to try to emphasize that already EDM experiments are probing masses above the range that the LHC hopes to reach. Experiments underway now at ACME and elsewhere expect to push these masses up by another factor of 3 or so within the next few years. And there are very plausible ideas to keep advancing if needed. You know, obviously the game changes if one of these next generation experiments actually detects a non-zero EDM for the first time. So with that, I'll stop and thank you for attention.